Right, okay. So students, now we are going to discuss the seventh RYM paper. So this is the discussion for the RYM paper 7. So there are good 10 MCQs in this paper as well. So let's go one by one. Okay. Question number 1. Number of electrons in the outermost energy level of the element with the atomic number 42. So remember, we wrote the electron configuration from hydrogen to barium. So therefore, you should be able to find out who is the atomic number 42, right? Can you guess the element? So atomic number 42 is nothing else but molybdenum, right? So molybdenum is special. It is having kind of a special configuration. Its configuration can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, then 4s2, 4p6, then 4d4 and 5s2. This is what we expect as the configuration of molybdenum. But we know that molybdenum's configuration is rearranging into 4d, 5 and 5s1 in order to obtain the greatest stability. So there is another element. We know that in the periodic table, if we analyze the periodic table, in the same group before molybdenum, we have chromium. So chromium also, this kind of a behavior can be seen in chromium as well. 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. In order to obtain the greatest stability, its configuration is rearranging in this way. So they're asking number of electrons in the outermost energy level of the element with the atomic number 40. So you can see that these are the electrons in the first principal energy level, second, third, fourth, and we know that outermost principal energy level is fifth principal energy level, n equal 5. So in the fifth principal energy level, there is only one electron. So therefore, we can consider that there is only one electron. Question number 1, answer is second one. Very easy. Question number 2. What is the basis of the modern periodic table? Yes, we have discussed this one. The periodic table is actually developed by, first of all, developed by Dmitry Mendeleev. We know that one. Actually, in the periodic table, the main basis is two factors. The first thing is actually atomic number. We know that there are 118 elements in the periodic table. So the periodic elements are arranged in that particular order. 1 to 118, there are 118 elements. And the next thing is electron configuration. Using the electron configuration only, the elements are classified in groups as well as in the periods. We know that there are 18 groups in the periodic table and 7 periods in the periodic table. So therefore, the main basic, right? The periodic table is made by based on two factors. The first one is atomic number and the other one is electron configuration. So please keep that in your mind. That's very, very important. Got it? So therefore, question number 2 answer is third. Question number 3. The set of quantum numbers 2, 1, 0 plus half represents, right? So we have discussed about the theories of the quantum numbers. Can you remember? So what is the theory point of this question? Let's discuss the theory point of this question. Quickly revise. So while discussing these papers, actually, the advantage is you can revise all the theories you have learned, right? So as the theory point, under the quantum numbers, we learned that what is meant by the quantum numbers quickly. So quantum numbers means actually the way of representing the location of electron, right? So we know that we can represent the principal energy level, sub energy level that electron belongs to, and the orbital type, last one, the spin of the electron, rotation of the electron. So therefore, we have 4 types of quantum numbers: N, L, ML, and MS. So these are the symbols. So N means actually principal quantum number, isn't it? So this is principal quantum number. So principal quantum number is representing the principal energy level. Next one is azimuthal, or else we can tell that angular momentum quantum number. Angular momentum quantum number. So it is representing sub energy level or the shape of orbitals also. And the next one is magnetic quantum number. Magnetic quantum number is representing the orbital type, right? For example, if there are 3p orbitals in the p sub energy level, we know that px, py, pz. These are the 3 orbitals in the p sub energy level, and they have arranged in different spatial orientation, right? So when you consider, so this is px, py, px, right? So for this direction we have pz in this way, right? So we can see that in the p sub energy level there are 3 different types of p sub energy levels. So we can assign the magnetic quantum numbers as -1, 0, +1 for them, right? That's the way that we assign magnetic quantum numbers. And the next one is spin quantum number. Spin quantum number is representing the rotation of an electron. We know that according to the Pauli's exclusion principle, students, in an orbital, the maximum number of electrons are 2. So if one is rotating to the clockwise, the other electron is rotating to the counterclockwise. Therefore, we can assign +12 or -12. So this is the summary of the quantum numbers. There are 4 types of quantum numbers. Principal quantum number is representing the principal energy level. Azimuthal or angular momentum quantum number representing the sub-energy level or the orbital, right? That means the shape of orbital. So by looking at the azimuthal or angular momentum quantum number, we can tell the orbital shape. And the next one is the type of the orbital. We know that in the p sub-energy level, there are 3p orbitals. In the d sub-energy level, there are 5d orbitals. So therefore, we can identify the type. So px, py, pz, -1, 0, +1. So that is orbital type. And the next one is spin quantum number representing the rotation of the electron, right? Whether it is +12 or -12, clockwise or counterclockwise. So this is the summary of the quantum numbers. Now let's go for the question. The set of quantum numbers 210 +12 represents a 2s electron, 1s electron, 2s electron, 2p electron, 3s electron, and 3s electron. What do you think? So this is the quantum number set they have given. If they have given you quantum number set, you should be able to identify, right? You should be able to identify what is the corresponding energy levels. So this is principal quantum number, principal energy level. So this is azimuthal quantum number representing the sub-energy level, orbital type, and the rotation. So therefore, we can say that second principal energy level, L equal 1. We know that for the azimuthal quantum numbers, we are assigning L values. If the sub-energy level SPD are given, so the ML values are 0, L values are 0, 1. So therefore, we can tell that this is 2p sub-energy level, right? That means it is representing 2p electron. So question number 3, answer is third. Very easy. Let's move for the question number 4. An atom in its ground state contains 30 electrons. How many of these are in orbitals with L equal 2? Right. Now look at this one, students. We know that the atom which has 30 electrons, what is it? Tell me, what is the atomic number 30 element? Zinc. We can tell that zinc is 30. If zinc is 30, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. So this is the electron configuration of zinc. So they're asking an atom in ground state contains 30 electrons. How many of these are in orbitals with L equal to? Just now we discussed that. Remember students, L means azimuthal quantum number representing the sub-energy level. So the sub-energy level number, quantum number they have given is 2. Right? Then you have to understand if it is L equal to, right, what you can say about that. Sorry. If it is L equal to, which sub-energy level is that? We can tell that if it is L equal to, definitely that one should be D sub-energy level, right? D sub-energy level. So we know that in the configuration of zinc, we can see the D sub-energy level only in the third principal energy level, right? In the first principal energy level, we have only S sub-energy level. In the second principal energy level, we have only S and P, right? When you go for the third principal energy level, S, P, D, 3 sub-energy levels are there. Actually, the D sub-energy level is starting from the third principal energy level, right? So therefore, we can tell that there are only 3D orbital in the third principal energy level. So therefore, how many electrons are there? In the D sub-energy level, we know that 5 orbitals are there, right? So 3D10 configuration, right? All the orbitals are filled with electrons. So therefore, 10 electrons are there. So question number 4, answer is fifth one, very easy. Let's move for the question number 5. This is related to the hydrogen emission spectrum. Let's see. Which of the following has an energy difference equal to that given by electron transition corresponding to the line obtained in the red region of the hydrogen emission spectrum? Right. So let's revise the theory that we learned under the hydrogen emission spectrum quickly. Right. So what is the theory point? Let's quickly revise the theory. Remember students, we know that when we draw the hydrogen emission spectrum, we obtain several series, isn't it? There are several series. N equal 1 here. Let me consider. N equal 2 here. 3, 4, 5, 6. Right? We know that all the electron transitions, electron went for the high energy levels. It is coming back to the low energy levels. When it is coming back to the low energy levels, these are the possible electron transitions to the first principal energy level. Look at this one. From high energy levels, electron is falling to the first principal energy level. If the electron is falling to the first principal energy level, the possible electron transitions is belong to the Lyman series. Lyman series belong to the ultraviolet region in the electromagnetic spectrum. That's how we learn. And the next one is Balmer. In the Balmer series, we know that Balmer series actually belongs to a visible light region in the electromagnetic spectrum. But remember, I told you that that is partly. Only the first 4 lines in the Balmer series belong to the visible light region. Other electron transitions are belong to the ultraviolet region, right? So the first electron transition, N equal 3 to 2, H alpha. H alpha is red color. Then next one, H beta, green color. Next one, H gamma, blue color. And the last line that we can see in the Balmer series is violet to purple color, delta, H delta, right? So this is Balmer series. So we can say that Balmer series, it is partly visible. Balmer series is partly visible light region. And the next one, we can say that we have Paschen series belongs to the IR region, infrared region. So this is Paschen, which belongs to the IR region. Try to understand. Lyman, Balmer, Paschen. Then we have Brackett and Fun, Humphrey. Likewise, we can continue the spectrum. Right. So this is enough for us because they're asking the which electron transition corresponding to the red region. So this is the red region. In the red region, we can see that n equal 3 to 2. Neither. We can see that n equal 3 to 2. So therefore, we can tell that directly. So n equal 3 to n equal 2 is the corresponding electron transition for the red color region. Understood? So they have given answers like this. The difference between the energies corresponding to the n equal 2 to 3, n equal 2 and n equal 3, yeah. The energy difference between that one. And n equal 2 and 4. No, n equal 2 and 4 is not related to the what? Red color region, that's wrong. Second one, 2 and 3. Again, they have given 1 and 3. Yeah, in this question, actually, we don't have the correct answers. Why? They have given two possible set of answers, but we know that the red color region, the red color is obtained when the electron is falling from the third principal energy level to the second principal energy. So therefore, the energy gap between n equal 3 and n equal 2 only representing the red color. Understood? The energy emitted by the electromagnetic radiation when the electron is falling from third one to second one, the wavelength or the frequency belongs to the red color. So therefore, we don't have any answer for this one. So therefore, let me consider this question as all because we don't have the correct answer for this one. Okay. It should be only n equal 3 and 2. Remember this one, students, hydrogen emission spectrum. This is very important. In recent past papers, I think 2022, 2023 also, they have given two MCQs. In the first 10 MCQs, definitely there will be one of them in the hydrogen emission spectrum. In the last 2 years, they have given hydrogen emission spectrum MCQs, right? So therefore, we have to be very careful for this one. Question number 6. In lithium, red line of emission spectrum has wavelength 671 nanometers. Energy of 1 photon is yes. So this is actually we learn under the electromagnetic spectrum again. How to calculate the energy of a photon. Can you remember the equation that we obtained as the theory point for this question? We know, students, according to Planck's theory, energy released or absorbed by an electron when it is transferring from one energy level to another energy level, that energy is directly proportional to the frequency. So therefore, in order to remove the proportionality symbol, we can put the constant, which is known as Planck's constant, equal h. So the Planck's constant value is 6.626 10 to the power minus 34 joule seconds. You have to remember this one. Later you remember this one. Then the next equation is equal nu lambda, right? Velocity of light is equal to frequency multiplied by the wavelength, and C is equal to 3 into 10 to the power 8 meters per second, right? So this is equation number 2. And we know that we can combine these two equations equal. Instead of mu, we can apply here C over lambda. Then we have equal HC over lambda. Remember, E is representing energy of a photon. Okay, you have to remember these things. If you want to find out the energy of photon mole, what you will do? You can multiply this one by Avogadro number. Then you will obtain energy of a photon mole, right? This is energy of a photon mole. Got it? Right. Now here in this question, they're asking energy of a photon. They have given the wavelength. Very easy. We can use here equal hc over lambda. Planck's constant 6.626, 10 to the power minus 34 joule seconds. Velocity of light is 3 into 10 power 8 meters per second. Divided by, what is the wavelength? 671 nanometers. We know that 671 nanometers means 671 10 to the power minus 9 meters. And we can write down this one as 6.71 10 to the power minus 7 meters, right? So we have done enough calculations. So we have done enough calculations in this topic in the theory class. So therefore, you have to remember how to do this kind of a simple calculation. Minus 7 meters. I told you that when you are doing, when you're dealing with this kind of a calculation, always follow 3 steps. Can you remember? First of all, deal with the units. At next, 10 to the power values. Finally, you can divide, simplify numerical decimal values. Okay. This is the way that you are going to simplify this kind of a calculation. Meters will cancel off, second per second will cancel off. So therefore, we can say that energy is equal to 6.626 multiplied by 3 divided by 6.71. 10 to the power minus 19 joules, right? So when you simplify this one, use the logarithms and find out the answer, you will have 2.96 10 to the power minus 19 joules. So this is the energy of a photon, right? So this answer is given in the second one. Question number 6, answer is second one. Right? So these are very simple calculations we discuss in the theories. Right? Shall we move to the next one? Right. Question number 7. In which of the following species has only one unpaired electron in the outermost energy level? So they have given sodium plus, copper plus, Fe2 plus, copper 2 plus, and Cr3 plus. Shall we write down the configurations quickly? Let's write down the configurations of these cations. They have given, all of them are cations, right? So therefore, let's write down. Sodium plus, copper plus, Fe2 plus, Cu2 plus, Cr3 plus. Sodium is 11, copper is 29, iron is 26, copper is again 29. Chromium here we know that it's 20. First of all, let's write down the elemental configurations. Sodium, sorry. Element configuration is 1s2, 2s2, 2p6, 3s1. Copper is actually 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. Its configuration is rearranging in order to obtain the greatest stability. Fe iron Configuration should be 3s2, 3p6, 3d6, 4s2. Again, Copper's configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1. What about chromium? 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. Now, let's obtain the cation configuration. So, after forming a sodium plus, one electron is removed. Copper plus, here one electron is removed. Fe2 plus, two electrons are removed. Copper 2 plus, here one electron, and this become 9. Cr3 plus, here one electron, two electrons are removed, then this becomes 3d3. So these are the configuration of the 5 cations. They are asking in which of the following species has only one unpaired electron. Students, you can see that here in sodium plus 0 unpaired electrons. No unpaired electrons because all the orbitals are completely filled. Look at copper plus, all the orbitals are completely filled. Make 3d10 completely filled. What about Fe2 plus 3d6? Shall we draw the orbital diagrams? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. According to the Hund's rule, always electrons are filling to the orbitals one by one, and the next one here. So therefore, we can say that unpaired electrons 4. What about 3p6, 3d9? According to the Hund's rule, first of all, electrons are filling to the each orbital one by one. Then the next opposite spin electron 6, 7, 8, 9. Here we have only just one electron in the orbital. What about 3d3? So in 3d3 we can see that there are 3 orbitals, 3 unpaired electrons. So answer for this one, following species has only one unpaired electron, copper 2 plus. Answer is 4th one. Question number 7, answer is 4th one. Huh? Very easy, electron configuration. Okay. Question number 8. What is the maximum number of spectral lines obtained when an excited electron of hydrogen atom jumps from n equals 6 to low energy levels? They're asking how many spectral lines can obtain if there are 6 energy levels. That means how many electron transitions will be there, right? So that's what they're asking. Okay, let's draw the energy levels and let's see. N equals 6. Here we have n equal 5, 4, 3, 2, and 1. Okay. So these are the principal energy levels. So this is the electron transition from n equals 6 to 1, 5 to 1. All the possible electron transitions from n equals 6 to the lower energy levels. How many spectral lines can be obtained? So in the Lyman series, we can see that 5 spectral lines are there because there are 5 electron transitions. Then let's go for the Balmer series. In the Balmer series, we can say that how many electron transitions? Less than one of Lyman series actually. Here we can see 4 electron transitions. That means 4 spectral lines. When you go for the Paschen, here we can see 3 electron transitions. Bracket 2, fun. So that means we can see that how many spectral lines can be obtained when there are 6 energy levels. 5 plus 4, 9, 12, 14. There will be total 15 spectral lines, right? If there are 6 principal energy levels, remember students, we can obtain 15 spectral lines in the spectral line diagram, maximum. Okay, then answer should be question number 8, second. Very easy. Question number 8, answer is second. Right? Okay, let's move for the next question. Question number 9. The number of subshells, orbitals, and the maximum number of electrons exist in the major energy level, that means principal energy level, which is represented by the principal quantum number n equal to. So this is very easy. N equal to means second principal energy level, right? If you want to obtain the number of sub energy levels in the second principal energy level, and if you want to obtain the number of orbitals and the total number of electrons in that particular energy level, you have only simple 3 general expressions. Number of sub energy levels can be obtained by the energy level number n, that means 2, because we know that if you go for the second principal energy level, there are 2 sub energy levels S and T. Therefore, the energy level number itself is actually explaining the number of sub energy levels. Then the orbitals. Orbitals can be obtained by n squared, right? Orbitals can be explained by n squared. N squared means 2 squared, the answer is 4, right? Is that correct? Yes. In this sub energy level, we have only one s orbital. In the p sub energy level, there are 3 orbitals. Total number of orbitals in that particular energy level will be 4. Then the total number of electrons in an each orbital, since there are 2 electrons, you can multiply this one by 2. Then 2n squared is given by is giving total number of electrons. 2 into 2 squared. Answer is 8. Look at this one. When the all orbitals are completely filled with the electrons, total number of electrons are 2 plus 6. Understood? So therefore, you can remember it. So this is some kind of a short note that you can remember. If you know the principal energy level, in order to find out the number of sub energy levels, orbitals, and the number of electrons in that particular energy level, n squared and 2n squared can be used, right? So 248, that is given in the second option. Second one is the answer. Very easy, right? Practice these kind of questions first of all, right? Later we can discuss difficult questions. In upcoming RYM papers, I will include 15 MCQs. Let's see. When you go for the second unit, third unit, we can include the number of MCQs greater than 10. Right? Right. Last question. That's also very easy. Sorry. Which of the following represent the electron configuration of the atom, which is isoelectronic with ammonia molecule? Students, look at this one. Ammonia molecule. We know that ammonia molecule is containing 1 nitrogen atom and 3 hydrogen atoms, isn't it? Right? Look at this one. number of electrons in ammonia. Only one nitrogen atom. There are 3 hydrogens. So nitrogen is actually atomic number 7. Hydrogen is 1. So therefore, 7 plus 3 into 1 is 10. That means in ammonia molecule, altogether there are 10 electrons. Right? Nitrogen is 7. So therefore, 10 electrons. Then these 10 means actually what is the electron configuration? 1s2, 2s2, 2p6. That means neons configuration. Right? So that means we can tell that ammonia molecule is isoelectronic with neon atom because the total number of electrons are same. Neon is containing 10 electrons. Ammonia molecule is also containing 10 electrons. Can you understand? Therefore, in this way, we can see that 1s2, 2s2, 2p6 is given in the second option again. Okay. Remember that students always in the RYM paper try to get always 908 out of 10, right? So keep a target like that. When I'm giving 15 MCQs, always keep the target to take 13 MCQs correctly or 14 MCQs correctly. Okay. Right. Okay. So then this is all about the 7th RYM paper, and we can discuss the next RYM paper in the next week class. Okay. Right.